Given the differential equation we're asked to solve, so somewhere down the line, we're supposed to give a function. So our answer will be a function. Okay. We're told that the first derivative with respect to time plus the original function equals t times e to the negative, and that should have been a t plus 1. Okay. So this is a t up here. All right, so how are you going to do something like this? Well, I claim this is a first order linear differential equation because, well, we're only dealing with the first derivative and the original function. So first order kind of makes sense. I claim it's linear. Let's see what we can do. All right, now what we learn is that if you have a differential equation of this form, you can analyze it in this way. So we'll call this P of t times the original function equals Q of t. All right, so now we have the first derivative times some other function times the original function equals some function, and everybody is in relationship to time. Okay, so time's ticking away for all of these. If you can rewrite your differential equation in this form, it's a first order linear differential equation. Okay, in our problem, what are our P and Q's? What are our P and Q's? So for this problem over here, we just had the coefficient of 1. So that's P of t equals 1. That's fairly easy. Over here, this is kind of ugly, so I don't know how this is going to play out, but this is Q of t equals this. So we have t e to the negative t plus 1. Okay, well, we've analyzed it. It is of this form, so what can we do? Well, that's when they say, if you can do this, then what you need to do is you need to find the integrating factor. Okay, so how do you do that? So mu of t is e to the integral of our p of t dt. Okay, in this problem, that's fairly easy to do. That would be e to the integral of 1 dt. Okay, well, the integral of 1 is just t, so we find that that's e to the t. That's not so bad. So this, I mean, how this happens is kind of magic, but so far it's not so bad. Now, what they say then is that you want to take this and multiply it times your original problem. And if you do that, you will be able to solve it. Okay? Well, that's what they say. Let's give it a try. So we're going to multiply our new integrating factor by the original problem. So we'll have e to the t, e to the t, e to the t. Okay. And we have y prime. We have the original y. And then we have equals t e to the negative t plus 1. And I better do parentheses because it's also times that 1 there. So you get another 1 there. All right. So we've rewritten the original problem in this way. And they say if you do that, well, it's going to be pretty nice for you. Okay. Let's take a look over here. So we have e to the t times t e to the negative t. Well, just from our exponent rules, that'll be t minus t. That's 0. So you're just going to get this t here. So just that t in the front. That's going to come out. And then you will get another e to the t there because it's going to distribute with that 1. So far, so good. We still have e to the t y prime plus e to the t y. Okay, so far so good. What can we say about this? Well, now we got to look at this and see what's happening. So what is going on with this guy? We have e to the t y prime, e to the t y. this reminds me of something. This reminds me of the product rule. So, with the product rule, and I'm sure you already know, but if you have two functions and you take the derivative, well, what's that? Derivative of the first times the second plus the first times the derivative of the second. Now, we don't care about order. We can switch up the order as we please. But that's what it looks like is going on over here. You have the original times the derivative of the second, and then you could call this the derivative of the first since it's e to the t, and it is its own derivative, and then y. So this looks like product rule to me. Okay, so that's good news. We kind of know how this works. All right, I'm gonna have to make some room for myself, but we know at least what's going on now. Okay, we identified that that is the product rule, so we could rewrite the left-hand side of saying that the derivative of e to the t y, right? That's the same thing. Okay, but what does that buy us if we do that? Well, kind of buys us a lot because now we can say, well, if you integrated that derivative that we just identified, e to the t y dt integral t plus, I gotta watch my t's and my pluses. Okay, so if we integrate this, well, it is what it is, right? I mean, it's the fundamental theorem of calculus right there. So it just kind of pops out there. So that's kind of cool. Now, what about this guy? We can break it up if we want because it's separated by addition. So because of the limits, because of limit rules, you can break this up. So that t is going to get an exponent of 2, but then we have to do the 1/2. So that's not so bad. E to the t is its own derivative. So that's not so bad either. My dog is scratching his own head and he's honking. Um okay, so that looks good, but you know what? We're going to get that constant of integration. Okay, that looks pretty good. Um, we only have one y there, so I would say at that point we're just about done. So let's see if we can't just divide. So if we divide everybody by e to the t, we're gonna get our one y. You are gonna get 1/2 t squared e to the negative t, and then you would get e to the t divided by e to the t. And so that kind of just looks like 1 to me. Okay, that looks good to me. So hopefully that's helpful.